In this example, we are going to put everything together that we have learned about the fundamental theorem of calculus so far. So putting all of those nuts and bolts together in one big problem. That's what we are going to try to do here. So g of x is defined as the integral from 0 to x of f of t dt. So notice the graph that we are presented with. This is the graph of f. This is not the graph of g. Okay? G is the integral from 0 to x, meaning function g represents the area underneath this curve, or the area between this curve and the x-axis. And so all of these questions I'm going to ask you about over here, notice these are all asking about function g. So I'm not asking you where is the function that is graphed, where is that function increasing, not function f. I'm asking you where is function g increasing. So that's a little bit different. So there's two ways of going about parts A and B, which ask about where the function g of x is increasing and decreasing. The first way to think about this is just to think of g as an area function. We are accumulating area between the curve f of t and the x-axis. So g would be increasing when we're gaining positive area. So if you think about just shading in the area, if I start at 0, and let's say I go from 0 to 1, I'm going to continue gaining positive area because this region is above the x-axis. So therefore g would be increasing from 0 to 1. So that would be one way to tackle question A. I'm going to say g is increasing on the interval, the x interval from 0 to 1. That would be the first interval where the area is increasing. However, notice what happens after I go past 1, from 1 to 2. This little region here is below the x-axis, so that means that area will be counted as negative. So I would be subtracting area. That would mean that the area would actually be decreasing. So the area doesn't begin to increase again until I begin gaining area above the x-axis, which is going to happen after we pass 2. And in fact, we're going to continue gaining area all the way from 2 to 9. So the second interval, where this g of x function, this area function would be increasing, would be from 2 to 9. So you can say we are increasing from 0 to 1 and also on the interval from 2 to 9. Now that was one way of explaining why we're increasing over those intervals, by thinking about the g of x function as an area accumulator. We're accumulating area. But let me attack this a different way, and this is going to help us answer some of the subsequent questions. Remember that a function, in general, any function, will increase when its derivative is positive. So let me say that again. Right? A function, we know, will be increasing when the slope is positive, so when the derivative is positive. So we could go ahead and analyze the derivative of function g. So that's taking the derivative with respect to x of function g, which is the integral from 0 to x of f of t dt. Now here's the fundamental theorem of calculus, part 1. Remember, when we differentiate and then we integrate, those are inverse operations. So the fundamental theorem of calculus part 1 says these are going to undo each other and we're going to be left with f of x. So this means that g prime, the derivative of g, is actually the function f. Now remember, whether we call a function f of x or f of t, in this case, function f of x is the same as the graphed function f of t. We're just interchanging the independent variable in this case. And we're answering now in terms of x because x was the upper limit of integration. That's the x value that we're ending at. So since the derivative of g is actually equal to f, and I'm going to put a bubble around this because this is pretty important, then we could say that g of x is going to increase when its derivative is positive. And since the derivative of g is f, then another way of answering this question is basically finding where is f greater than 0. That means I'm looking at the graph and I'm finding what part of the graph is above the x-axis. So if I were to just highlight here the parts of the graph above the x-axis, you'll see that those are the pieces of the graph from 0 to 1, as well as from 2 to 9. So that's an alternative way of answering where is this g of x function increasing, and we can use the same strategy for where the function is decreasing. We know that a function is going to decrease when its slope is negative. So since the derivative of g is f, then this is like asking where is f less than 0? Or where is this graph below the x-axis? And there's only one little piece of the graph of f that's below the x-axis, and that's from 1 to 2. So g of x will decrease on the interval from 1 to 2. Next, let's find the x values of the local minimums of g. Again, let me clarify that all of these questions A all the way down to J, these are all questions about function g of x, which is the integral from 0 to x of f of t. So where do we have a local minimum? So if we think back to when we first studied minimums in general, minimums occur when the derivative of the function goes from negative and changes to positive. So again, a minimum is when the derivative or the slope changes from negative to positive. So I need g prime to change from negative to positive. But since g prime is actually function f, it's like asking where will this graph of f change from negative to positive? In other words, where do the y values change from negative below the x-axis to positive, which would be above the x-axis? And that's going to happen here at x equals 2. So you see at x equals 2, we have on the left side we have negative y values, on the right side we have positive y values. So this function is going from negative to positive, but since f of x is actually g prime, then that means that at x equals 2, the derivative of g is changing from negative to positive, and that's what creates a local minimum. Now, using this same logic, we know that function g will have a local maximum when the slope of g, or the derivative of g, changes from positive to negative. So since g prime is function f, we're looking at where does function f change from positive to negative. And that would occur at x equals 1. At x equals 1 here, we see that the y values change from positive above the x-axis to negative below the x-axis. So we're going to have a local maximum at x equals 1. Part E asks for absolute maximums, or I should say 1. Where is the absolute maximum? And what makes this, again, such a great problem is now we're digging way back to the beginning of our study here, which was about the extreme value theorem. So we have to remember that when we're looking for absolute maximum or minimums, we want to consider the endpoints. So I've made myself a little note here for parts E and F to be sure that you check the endpoints. So we know that we have a local maximum at x equals 1. And so now we need to look at the endpoints, which would be at 0 and 9, and see if either one of those is going to actually be a larger value. So let me go below here. I'll shrink this down just a little bit. And let's actually compute some of these values, or I rather should say we're going to estimate them. So for example, we had a local maximum at x equals 1. So let's think about what would g of 1 actually look like. So since g of x is the integral from 0 to x, and we're plugging in 1 for x, then we're going to integrate from 0 to 1. You're just plugging in 1 where you have an x. So g of 1 is the integral from 0 to 1. So if you look at your graph and think about accumulating area from 0 all the way to 1, we have a nice region that's above the x-axis. So we expect g of 1 to be some sort of a positive number. It's a positive value. But now we want to also consider the endpoints, 0 and 9, and see if either of those is a larger positive value, which would make it bigger than g of 1. That would make it the absolute max. So let's consider the left endpoint, which is at 0. So let's find g of 0. That's the integral from 0 to 0 of f of t dt. But we know if we're starting at 0 and ending at 0, then we really don't have a region to compute the area of. So g of 0 is actually just equal to 0. So that's going to be smaller than g of 1. And then let's do the same thing and see about the value at the right endpoint, which would be g of 9. So that's the integral from 0 all the way to 9 of f of t dt. So now think about starting at 0 and accumulating area all the way to 9. So we know we're going to subtract off just a little bit of area here between 1 and 2, but then we are going to gain a bunch of area from 2 to 5, and then we are going to gain way more area here from 5 to 9. So if we take all of the area between the function and the x-axis from 0 to 9, we are going to be getting a much larger positive number than the area that we accumulated from 0 to 1. So that tells me that at x equals 9, we're actually going to have our absolute maximum. That's going to be the largest y value on the curve. So now let me pause for a second, because you'll notice the very last question this asks of us at the very end, part J, it's going to ask us to see if we could sketch a graph. So let's take what we have so far, where we have our local minimums and local maximums, and we just found an absolute max, and let's begin to put together our graph. So I'm going to go below just for a second here, and I'm going to go ahead and include my tick marks along the x-axis, and we need 9 of those. So I'm going to kind of spread mine out nicely, and I recommend that you do the same. And let's begin to plot what we have so far. So from above, we said that g of 0 was equal to 0. So we're going to actually plot that point. That means that we will plot 0, 0 on our graph here of g. Then up above, we also said that g of 1 here was a positive number. So when we plot our point at x equals 1, we're going to plot a positive y value. And now you're going to notice I am not going to actually put any tick marks along my y-axis because I'm not sure exactly how large that number is. I'm just going to go ahead and plot it as a positive, but I am going to make a little note to myself that this was a local max. We said we had a local max at x equals 1. And then let's go ahead and plot what we know is happening at x equals 9. Because g of 9, we said, was our largest positive value. So over here on the right endpoint at x equals 9, I'm going to go ahead and plot my largest y value. And I'll make a little note to myself that this was my absolute maximum. Likewise, I could also make a note at 0, 0 that that was my absolute minimum. And you know what? We didn't discuss that. Let's talk about why. Why would we have an absolute minimum at 0? Because that was actually the next question. Part F says, where's the absolute min? So we have a local min, we said here, at x equals 2. So then we would also need to consider the endpoints and see if one of the endpoints gives us a smaller value. So you'll see I'm going to do a lot of erasing as I shade underneath my curve, and you may find you have to do the same. Just shade lightly in pencil and then kind of erase. So we already computed g of 0. G of 0 is 0, and then g of 9 is a large positive number, the right-hand endpoint. So let's compare the value at the local minimum, which was at x equals 2. So because I'm running out of room, I'm just going to erase one of my little integrals here, and you can just add on somewhere else. Let's compute g of 2 and think about the value at 2. So that's the integral from 0 to 2. And what kind of a number would we get if we generate area starting at 0, so here I am back to shading, and going all the way to 2? Is this going to be a positive or a negative number? Because the area above the x-axis is much larger than the area below the x-axis from 0 to 2, we know that this is going to be a positive number. So when we're trying to figure out the minimum, whether it occurs at x equals 2 or whether it occurs at the endpoint. In this case, you can see that we have a smaller value at 0. G of 0 was equal to 0, whereas G of 2 was a positive number. So the smaller of these is going to be 0. So that means we have an absolute minimum at x equals 0. And that corresponds with what we just graphed on our curve below. So now let's move on to concavity. So when we discussed concavity in the past, when we wanted to find where a function was concave up or concave down, we needed to look at the second derivative. So if I'm interested in where g of x is concave up, I need to get some information about g double prime. Well, look at what I have written in our previous bubble. We said that g prime was equal to f. So if we take the derivative of g prime, which will give us g double prime, that means g double prime is actually equal to f prime. So g double prime, the second derivative of g, is actually equal to the first derivative of f. Another really important piece of information. So when I'm trying to figure out where function g is concave up, ultimately I'm trying to figure out where the second derivative of g is positive. Then that will be where g is concave up. But the second derivative of g is actually the first derivative of f. So I'm really looking for where f prime is greater than 0. Where is f prime positive? And so the graph that we're looking at is the graph of f. So therefore, I'm being asked to analyze where is the slope of this curve positive. So now we're not looking at the area under this curve, we're actually looking at the slope of the curve f. So where do we have a positive slope? So it looks like we have a positive slope from approximately maybe 1.5, you might estimate that. This little stretch of the graph, from 1.5 to a little bit past 3 is where we have a positive slope. So that means that the graph of g would be concave up from about 1.5 to about, I'll call it 3.2. So we are concave up on an x interval from about 1.5, and again I'm just estimating here, to approximately 3.2. And then that would be again concave up from 5 all the way to approximately 8. So the interval from 5 to 8, that would be the second interval where f prime is greater than 0, which means g double prime is greater than 0. So again, same logic there. If we're looking for concave down, we know a graph will be concave down. G is concave down when its second derivative is negative. Since g double prime is f prime, then we're really looking for where f prime is negative. That's the slope of this curve. Where do we have negative slope? So we have negative slope from 0 to about 1.5. Then we would have negative slope again from about 3.2 to 5. Let me highlight these regions for you. So again, negative slope for this first piece from 0 to about 1.5, and then again here from about 3.2 to 5. And then again, the last piece of this graph here looks to be about from 8 to 9. So let me get all those intervals here listed. From 0 to 1.5, from about 3.2 to 5, and then again from 8 to 9. So there are 3 intervals where the graph of g would be concave down. And then lastly, we're looking for values, x values of inflection points. So where is the concavity changing? And you can just look at your intervals of concavity and see where the concavity changes. But this is essentially like asking where does the second derivative change sign? So where is f prime changing sign? Where does the slope change from negative to positive and vice versa? And so the slope is going to change sign a bunch of times actually, at 1.5, at about 3.2, again at 5, and one more time at 8. So we would have 4 total inflection points. A total of 4 inflection points. So now the challenge is putting all of these pieces together to try to complete our graph. And I am going to need some of this information. So I'm going to keep my concavity where I can see it. I'm also going to need my inflection points here to try to fill in the rest of our information. So I graphed my local max and my absolutes. I notice I actually didn't graph my local min. So if you look above, we had a local minimum at x equals 2. And I wrote down the information here. We did find g of 2, and we said it would be a positive value, but we didn't actually graph it. So g of 2 is going to be a positive, so let's go ahead and graph that. And it's going to be above the x-axis. It's not going to be obviously bigger than our local max, so I'm just going to graph it somewhere in here. So it's positive, but it's a smaller number than our max. And I'm just going to mark it as a min so that I remember that I have a local min. Then let's look at these IPs. Let's look at these inflection points. So we've got an inflection point at 1.5. So if we were to compute the value of g of 1.5, that would be the integral from 0 to 1.5 of the function f of t dt. So going back to our original graph, let's accumulate area from 0 to 1.5 and see whether or not we get a positive or a negative value. So if I were to go back to my function and begin accumulating area from 0 all the way over to 1.5, I know I'm going to have a positive overall result because all that area is lying above the x-axis. We're only subtracting this itty-bitty little piece of area there. So we know that that area is going to be something in between the area that we have from 0 to 1 and then the area we have from 0 to 2. So we can graph our inflection point at 1.5. It's going to be a y value that's somewhere here in between our maximum and our minimum. So I'm just going to put a little IP there. So let's begin to fill in our concavity. So we know that the graph begins concave down. It said from 0 to 1.5. So let's go ahead and graph something concave down until we get to that inflection point. And now we're going to change to concave up. And we're concave up all the way until, from 1.5 until 3.2. So let's think about what kind of a value we're going to have at 3.2. So what's g of 3.2 going to look like? The integral from 0 to 3.2 of f of t dt. So again, start accumulating that area all the way from 0, but this time let's go all the way here to 3.2. See how this is adding on area above the x-axis. So we're going to continue adding positive area. So g of 3.2 is going to be even bigger than our value, which was at g of 1.5. So this is going to be a larger positive number, I'll just say. So at 3.2, I'm going to graph an inflection point that's a little bit larger than our maximum we had before. That's our next IP. And in fact, if you continue looking at g of 5 and g of 8, we just keep adding more and more area. So if you want to go ahead and plot at x equals 5, our y value would be just a little bit larger than the previous inflection point, its y value. That's another IP. And then lastly, all the way over at 8, we have even larger y value, but not quite as large as our absolute maximum. And once you have those inflection points graphed, then you can just start to graph in the concavity and show that it switches at each of the inflection points. So we're going to be concave up from 1.5 all the way to that next inflection point, which was about 3.2. Then the concavity changes to concave down like a frown here from 3.2 approximately to 5. Then we're going to have this big stretch where it's concave up, and it's going to be a very gentle concave up like a cup, we always say. And then it ends, this last little piece here is concave down. I always do these in pencil because sometimes I sketch it out and then have to go back over it to really make the concavity match. but this would be an accurate graph of g of x. We've graphed g, where the y values on this curve that we just graphed, these y values are representing the integral, or the area, under the curve starting at 0 and ending at any x value. So now you can see 25 minutes later why this is such a big task, kind of putting it all together. But it really does require us to understand integrals and the fundamental theorem of calculus, both parts, to put all these nuts and bolts together.